Descending flight. For an engine-supported descent, when the available thrust is less than the thrust required for level flight, the aircraft will descend and maintain constant indicated airspeed. The absent thrust is balanced by a component of weight. In gliding flight, there's a total absence of thrust, i.e. the weight component is the only component counteracting drag. If drag increases, the descent must be made steeper in order to maintain speed. In other words, drag determines the descent angle. In the descent, the force opposing lift is weight cosine descent angle, and the force acting on the flight path is weight sine descent angle, which are the same as the formulae for climbs. Gliding for maximum range. To glide for maximum range, an aircraft must descend at its minimum gliding angle. The ratio between distance travelled and height lost is exactly the same as the ratio between lift and drag. Therefore, maximum glide range occurs when the lift to drag ratio is maximum. In the above graphs, for an angle of attack of 4 degrees, this will give the maximum gliding range. It's a tangent between CL and CD. Maximum gliding range will be with the minimum or least glide angle. The polar curve. A polar curve shows the variation of CD as a function of CL. It shows how much drag is produced for a given point. It shows how much drag is produced for a given lift at every angle of attack. Each point of the polar curve is obtained for a given angle of attack and shows the corresponding values of the coefficients of lift and drag. Point A is between VMD, the velocity for minimum drag, and the maximum speed, and has the minimum drag coefficient. Point B is the point at which a tangent from the origin touches the polar curve, which is at the point at which the total drag is minimum, the lift to drag ratio is maximum, and the indicated airspeed in level flight is VMD. This is also the speed at which the longest glide distance will be achieved. Point C falls between VMD and VS, stall speed, and is approximately VMP, which approximates to the speed of Vy for a piston propeller aeroplane and indicates the value at which the minimum sink rate will occur. It's the speed that will attain the maximum endurance during a descent. Point D is where CL and CD are both maximum, and the point at which the minimum speed in level flight, the stalling speed, Vs, is attained. Gliding for maximum endurance. To maximise endurance, the aircraft must descend at the lowest possible vertical speed. From the diagram, V sine descent angle must be at a minimum. This occurs at the speed where power required is at a minimum. Note that the speed for maximum endurance is always less than the speed for maximum glide range. Maximum endurance speed gives a steeper glide path than maximum range speed. The effect of external factors on the glide. With flaps deflected, glide angle is steeper and best gliding speed is slower than flaps retracted. This is a drag effect. Weight does not change the maximum lift to drag ratio. However, the speed at which the aircraft must be flown to achieve the maximum lift to drag ratio increases. When gliding into a headwind, the best gliding speed, i.e. the speed for maximum range, is greater than when gliding in still air. When gliding with a tailwind, the best gliding speed is less than when gliding in still air. Gliding for maximum endurance. The vertical velocity must be at its least. Descent speed along the flight path must also be low. The glide angle must be low. The distance travelled is irrelevant, so the speed to fly at is less than VMD. It corresponds to VMP and is close to CL max. Mass directly affects gliding endurance. For heavier masses, both the rate of descent and equivalent airspeed increase, which reduces gliding endurance. Wind does not affect endurance.